Right, 7 participants time. Okay, let's start. I don't need a silly horn. Right, so welcome to the first session of the second day. First, our invited speaker, Sean Moss, who is an assistant professor here, is going to talk to us about the Markov category of a random graph.
Okay. Thank you very much. Many thanks to the organisers for the invitation. Okay. The first thing to say is that everything I'll say this morning will basically be a subset of this work, which is with several other people. So my co-authors, Nate, Cameron, Eunice, Yatsuk, Dan, Sam, Hongsuk. See here for references and for correct statements. So the motivation was to look at this concept of a random graph, or slightly more precisely, a graph on, and connect it to Markov categories. So Markov categories we think of as a model for programming with probabilistic programming features. Graphons are sort of, one way to think of them is that they're a model of large graphs which you access by taking random samples. So if I have a graphon, I can think of writing programs to investigate it. And I can think of the equations between those programs as giving me a Markov category. And that's the thing we wanted to make precise. Unfortunately, I won't get to talk about nominal sets today. Okay, so in order to explain what's going on, I'll have to tell you a little bit about graphons, and I will not do justice to them. So if you want to learn really like what they are, this is a good starting point, this book. Okay. So large networks and graph limits. Okay. So an outline. So the first thing I'll do is I'll try to explain to you just enough of what these things are so you can get a feel for what's going on. I'll try to keep this accessible and recap very basic probability theory over finite sets from a categorical point of view, and give you the first correspondence between random graph models and something in category theory. In order to actually do programming, we need to use Markov categories, which I'll recap as well. But we need a bit more than Markov categories. We need distributivity and something that we call a Bernoulli base. Okay, so I'll introduce those to you. And finally, I'll show you how exactly we get a correspondence between certain structured Markov categories and random graphs. Okay. So, to be clear, in this talk, a simple graph is a set of nodes and an edge relation, a binary relation on those nodes, which is symmetric and irreflexive. So there are no self loops and there are no multiple loops, and it's not directed, it's symmetric. And some notation, I'll write G sub n for the set of simple graphs whose node set is 1 up to n. Okay, so there are 2 to the n choose 2 of those graphs for each n. Okay, everything okay so far?
Sorry, can you speak a bit louder?
I can try.
Where is the microphone?
Is there a speaker?
I think so. Yeah, the microphone does work. If you'd like to equip it.
Okay, I'll try talking louder. Okay, I might run out of voice, but we'll see. Okay, so here are some. Here's an example of a simple graph. Okay, so there's actually a simple graph for each theta. So fix an angle theta. The node set of my graph is going to be all the points on the sphere. And I'm going to say there's an edge between 2 points on the sphere if the angle that they close between them is less than theta. Okay, so that's just a graph. What I've drawn here is a little bit of the graphs. In the case, theta is pi over 3 and theta is pi over 6. Okay. So as you can see, well, actually these graphs are basically the same, right? Because they both have an uncountable number of nodes. Every node has an uncountable neighborhood. So is there really a difference between these things? Well, sort of, if we remember a bit more than just that it's a graph. So the sphere has a uniform distribution. If I randomly sample some points on the sphere, I can look at the induced subgraph that they give us. And for different angles, I'll get a different pattern of induced subgraphs, right? So in the case that the angle is slightly larger, I'll get a slightly more connected graph when I randomly choose points. And when the angle is a bit smaller, I'll get something a bit more disconnected. So one thing you might imagine doing is knowing that you have a model of a system which is a graph on a sphere like this, and there's an angle that you don't know. You could try sampling some points, seeing how connected the graph is, and then trying to work out what the theta was. Trying to infer the theta from the statistics of the graph. Okay, so this is kind of a quick motivating example. Right, so a bit more formally, what is a graphon? So a graphon is short for graph function. So it's a function that gives you a graph. First of all, it consists of a probability space. So a set omega, the sigma algebra on omega, don't worry too much if you don't know what that is. As long as you think you know what a probability measure on a set omega is, it's okay. So the idea is that this is like a set of nodes and a uniform distribution on them. And secondly, we need an edge relation. So you might expect the edge relation to be a matrix whose rows and columns are both omega and which is valued in 0 and 1. Actually, I'm going to take the unit interval here, and the reason isn't going to be clear immediately, but so the intuition will be that to sample a subgraph from a graphon, you use mu to take some the choices of node, and then you use the function w to check whether there's an edge, and the number you get between 0 and 1 is the probability that there was an edge. So it's a bit simpler to understand when it's just the set 0, 1, not the interval, like in this example, but we will need the more general thing a bit later. Okay, so this is just the example I had on the previous slide. Omega was the sphere, mu was the uniform distribution, and the adjacency matrix just tested the angle between two things. Okay. Another simple example is I take any finite graph, not necessarily simple. I can let omega be the set of vertices in that graph, and let mu be the uniform distribution on finite set of vertices, and I take w just to be checking whether there's an edge. Okay. So this no longer exactly represents the graph G because, well, we're modeling large, simple graphs. But the idea will be that we kind of want to pretend that this is an atomless measure. So if we take two samples, we're definitely not getting the same thing twice. So this is just a way of representing a very large graph using a finite bit of data. It doesn't exactly embed the finite graph into our model of large graphs. Okay. One thing to note, which is unfortunately quite important from a practical point of view, graphons model dense graphs rather than sparse graphs. So a dense graph is one where, say, if I look at this, the neighborhood of every point is sort of a positive fraction of the whole thing in terms of the uniform measure on it. If you look at actual graphs like the social network graph of the world, most people have a fairly small neighborhood rather than a dense one. That's just a problem. The theory is nicer for dense ones than for sparse ones. The sparse ones, there is a growing theory, but we're only going to talk about dense ones today. Okay. And another thing to note is that equivalence of graphons is quite non-trivial. So I can have two completely different probability spaces and different W's, but I might still want to think of them as the same large graph. And they're the same large graph if they induce the same finite subgraphs. One more thing I'll just mention quickly is that usually graphon means the special case where you're restricted to omega being the unit interval, but it doesn't matter for us, so I'll just let omega be arbitrary. Okay, so just to recap, graphon is a space of vertices with a uniform measure on it and a sort of probabilistic adjacency matrix. And we sample, so given a graphon, we get a distribution on each of these set of simple graphs on n vertices by sampling a vector of nodes and then deciding whether there's an edge with this probability. So if you prefer the formula, it looks like this, but I think the operational thing is a bit easier. Okay, here's another view on graphons. So a random graph model is a sequence of distributions on finite simple graphs. So Pn is a random simple graph on n vertices, which has the following properties: exchangeable, consistent, and local. So exchangeable means that if I commute the vertices of the labels, or commute the label set, I don't change what the distribution was. Consistent means if I marginalize out by dropping one of the vertices, say I sample a Pn plus 1 and I forget one of the vertices, then that should be the same distribution as if I just went straight to choosing something from Pn. And finally, locality means that if I pick a graph with h plus k vertices and I look at the first h and I look at the last k vertices, I get two simpler graphs, two smaller graphs. The distribution on those, they should be independent of each other. And they should also agree, by consistency, agree with the pH and the pK. Okay. So every graphon gives rise to a random graph model, right? By the process described here, this process gives you something that satisfies these conditions. Conversely, if I have a random graph model, I can get a graphon, but it's slightly non-trivial. So we're just going to rely on the fact that that is possible today. Right. A little aside, so as well as sampling finitely many vertices, we could have sampled countably many and then got a distribution on countable graphs. We won't do that today, but you can think of a graphon as giving you a random countable graph as well. Another motivation for considering graphons was graph limits. So if you take a finite graph and then look at this sort of homomorphism counting function normalized. So if you take this says, given a finite graph G, for every finite graph H, I look at the number of vertex functions which happen to be a homomorphism. Okay? This turns out to uniquely determine G. That's a non-trivial fact. But now this is a compact Hausdorff space. So what's the closure of the image of this? And it turns out you can represent the points in the closure of the image by graphons. So there's another way that graphons arise. We won't need to worry about that either. Okay, something some of you may have come across before, because it's quite a popular thing in sort of basic maths, is the Rado graph. So you can say concretely what it is, but it's easiest to say it's the unique countable graph with the extension property. So the extension property says, if I take two finite disjoint sets of nodes, then I can always find another vertex X, which is connected to all ones in the first set and none of the vertices in the second set. So if such a graph exists, then it's unique because there's a simple back and forth argument. Take a finite isomorphism, finite partial isomorphism, and you can always arbitrarily extend it by picking another point in one and then using the extension property to find something that matches it in the other. Okay, one reason that is interesting is the following. So here's a simple graphon. So first I fix a parameter alpha between 0 and 1. I take my omega to just to be the 1-point space, so trivial measure on that. And I take W alpha to be the thing which just says there's an edge between star and star with probability alpha. If I sample the countable graph from this graphon, then with probability 1, I get the Rado graph. And I kind of mentioned this just to connect this to something you may have already seen, and also to point out, even though you get the same graph every time you sample, these are different random graph models. Because if I look at the finite sample graph on n vertices, say for alpha, this is the formula for the chance I get a graph G. The bigger alpha is, the more likely I am to get a graph with lots of edges. Okay? So even though the isomorphism type of the countable graph is the same for all these random graph models, they're different because the bigger alpha is, the more dense those things are. And another thing to note is that this one is impossible to present with a graphon that only takes values in zeros and one. It's not completely obvious, but it is an interesting fact that you can't use 0-1 graphons to present everything. Okay, so to summarize, graphon is a probability space representing nodes with a way to choose a uniformly sample a vertex and a sort of probabilistic adjacency matrix. And a random graph model is a sequence of distributions of finite graphs satisfying three properties. I mentioned that you can't always represent a random graph model with a graphon where this is only the set 0-1. Sometimes you do need to take intermediate values. But we're going to see, we can pretend you always can take 0-1 if you consider graphons in arbitrary Markov categories, not just in the classical one of the Giri monad on measurable spaces. Okay. Okay, so probably most of you already know this, but I just want to be clear and make sure we're on the same page. So I write fin for the skeleton of the category of finite sets and functions. So then there's a functor in fin to set. which takes n to the set of finite set of distributions on n. So call this the finite distributions functor. So the set with n elements goes to vectors of reals, n vectors which sum to 1 or non-negative. As many of you know, probably know, this gives you a monad on sets. So I'm going to think of this as a clone, or I mean, sometimes abstract clone, but I'll just say clone. So the structure of a clone is essentially has a unit of a monad and has a bind. Okay, so the unit we'll say, given a pure element of n, I pick out the distribution that concentrates all the measure just on that point. So essentially quality testing. Bind says, given a distribution, say distribution on m elements and m distributions on n elements, I want to sequence those together to get a distribution on n elements. So the way to think of it is you first sample something between 1 and m, you check which one you got, and then you access the measure that comes from this here, and then sample something from 1 to m and return that result. So in terms of a formula, it's just this. So clones are equivalent to finitary monads on set, and the correspondence is you left Kahn extends the this functor to an endofunctor on set. Also note, if you start with just this structure, you can derive the functor structure. So it's really the clone that is the fundamental thing. Right, so a clone is commutative if we can reorder operations that don't interact with each other. So suppose I take a distribution on m elements and a distribution on n elements. So the way to read these things is first use the distribution alpha to sample something without using the result. Now check beta and return the first result and the second result, versus sample from beta without using the result, sample from alpha, and then return the second result and the first result. So those things are the same in the distribution monad, distribution clone. And when that's true for all alpha and beta, we call the clone commutative. Now, when a clone is commutative, we can define alpha star beta to be the common value of these two sides. And that has a type that looks like this. And that makes a clone into a symmetric monodal functor. So for finite distributions, actually a bit more is true. It's lax monoidal on the binary case, and it's strong monoidal on the nullary case. So D1 is isomorphic to 1. Intuitively, you can think of this as saying that if I take a sample and then I don't use the result of that sample, that's the same as if I'd never taken the sample at all. So all measurements are discardable. Okay. And whenever I have a monad, I can get a Kleisli category. So I'll write Finstock for the Kleisli category of D. So the objects are finite sets. Concretely, the maps from M to N are matrices valued between 0 and 1, such that the columns, the rows sum to 1. One of them sums to 1. In composition of maps, it's just matrix multiplication and the Kleisli category is symmetric monoidal. That comes from the fact that we had the fact that D was symmetric monoidal. That becomes the fact that the Kleisli category is a symmetric monoidal category, and the tensor is given by the pointwise product of matrices. Okay, so let's return to random graph models and try to analyze this a bit. So first of all, a random graph model is a sequence of distributions on GM. So another way to see that is just it's a sequence of maps in Finstock. Okay. So a map from 1 to an object in Finstock is the same thing as a distribution on that set. Okay. Let's look at the first two conditions, exchangeability and consistency. Okay, so I have to let Ing be the wide subcategory of thin, whose morphisms are injections. So objects are finite sets and maps are just injective functions. This notation G sub n extends to a functor from injop into thin. Okay, so n goes to the set of simple graphs whose vertex set is 1 up to n, and the action of an injection is to permute the nodes and forget some nodes. right? So I have a diagram in fin, which I can post-compose with the inclusion into fin stock to get a diagram in fin stock. And now a cone on this diagram with apex 1 is exactly the same thing as an exchangeable and consistent sequence. Okay. So the exchangeability condition just says that this is a cone for the bijections in Ing, and the consistency condition says that this is a cone for the sort of the one of the injections in Ing. Okay, and the third condition, locality, we can also describe this in terms of our cones. So finite sets is symmetric monoidal with coproduct. The category Ing is also monoidal, but it's no longer a coproduct, but it's still a tensor on Ing. This functor from Ing up to fin is oblax monoidal. So that means there's a map that takes gm plus n to gm times gn. All you do is you take a graph on n plus n vertices, you restrict to the first m to get a graph here, and you restrict to the last n to get a graph here. Okay. Now, a cone over that diagram is a monoidal cone if and only if your random graph model satisfies the locality condition. So what does a monoidal cone mean? It means if I map into gm plus n, and then I use the oblax monoidal structure to go here, that's the same as if I'd taken the cone at gm and the cone at gn, and then used the symmetric monoidal structure in fin stock to get a distribution on gm times gm. And the symmetric monoidal structure just takes two things, two distributions, and gives you the independent product of distribution, the product measure. So to say this is monoidal means that the two marginals are independent. Okay. Right. So let's consider cones a bit further. So the set of cones is the limit in sets of this, which I can rewrite first using the Yoneda lemma. It's the limit over of the natural transformations from a representable T. And I can use the property of colimits to move this inside. So cone is the same thing as a natural transformation from this functor to the functor D. So I'm going to make this a definition, curly G, define it to be the colimit of these representable functors over this diagram in job intersect. And now G happens to be a commutative clone. So the bind is, okay. So clones are the same thing as algebraic theories. So we could present this as an algebraic theory with operations and equations. And if we did that, we would say for every n, there is an operation whose arity is the size of the set of graphs on n vertices. And intuitively, the operation says, give me all my arguments. I have one argument for each possible graph on n vertices. I'm going to sample a random graph from my random graph model and then return the argument which was put in that slot. So, right, so GM says, make a choice of m from 1 up to m by sampling a graph on h vertices and then applying this function. So to sequence these things together, it's a bit complicated, but I've got m ways to choose n things from sampling a graph. I can just choose the k to be the same for all of these, and then I can bunch them together. I can think of sampling h and sampling k as just sampling one big thing, and then forgetting the two halves. Details are a bit fiddly. Okay. So not only is it a commutative clone, so being a commutative clone, it is therefore a symmetric monoidal functor. And it turns out that the cones in here that are monoidal are the same thing as the functors here that are, so the natural transformations here that are monoidal natural transformations. But I said they were clones, and all I've done is constructed a monoidal natural transformation between clones. But something very funny happens in these particular clones, which are commutative with with T1 being 1. The funny thing is that the clone structure is actually determined by the symmetric monoidal structure. So if I want to bind two things together, I can write that in terms of the monoidal structure and the functorial action. And the unit part of the clone is just given like this. Which means if I have a monoidal natural transformation, then it's already a morphism of clones. So a random graph model is the same thing as a morphism of clones from this particular clone G to D. Or if you like, I've got two monads on set and a morphism of monads between them is the same thing as a random graph model. Okay. Right, but we haven't really done any programming yet. So to do programming, we'll talk about Markov categories, which I'll recap now. Okay, so probably some of you already know this. I won't, hopefully you'll be able to understand if you haven't seen this before. I won't rely exactly on this definition. I will present it first just to neatness, and then I'll give you a slightly different definition that I'll actually work with, which is easier to construct examples of. Okay, but I'll talk you through this first. So a Markov category is a symmetric monodal category where every object is equipped with the structure of a commutative comonoid. So that means it has a map copy from x to x tends to x, and a map discard from x to the unit. The copy and discard maps are compatible with the monodal structure. This is actually a bit fiddly to write down, so I've omitted what it means. The discard maps are natural, which is another way of saying that the monodal unit is a terminal object. So sometimes we'll introduce this by saying C is a semi-Cartesian monodal category, an affine monodal category or something. Okay, but here's the point. So the basic fact is that there's a wide subcategory of deterministic maps. So those maps F that satisfy this equation. What does this say? It's saying if I do F twice, okay, if I take the input to X, if I copy it and do F twice at this side, that's the same as if I just did F once and then copied the result. So in other words, F does the same thing every time I run it. Because the discard maps are natural and I is a terminal object, the sort of companion equation to this always holds. One says, if I run F and don't use the result, that's the same as never having done F. Another way of saying that is that intuitively, all processes terminate. You never get a process that doesn't terminate and that blocks everything else. Okay. Because of the way this compatibility is set up, this subcategory of deterministic maps is a subcategory and it's Cartesian, which means it has chosen finite products. Okay, and the inclusion of the wide subcategory, which is identity on objects, is a symmetric modal functor and actually a strict modal functor. It strictly preserves. I mean, the chosen Cartesian structure that I choose here is such that it goes strictly to the original monodal structure here. So in some ways, the point of this definition is to have a symmetric monodal category with a terminal unit that has a map from a Cartesian category into it. Okay. So I tend to think in terms of something like this. So start with a Cartesian category V, V standing for values, if you like. So a throwaway definition here. A probability theory over V is an identity on object symmetric strict monodal functor into a symmetric monodal category whose unit is a terminal object. Okay, this gives you back a Markov category because in V I've got the diagonal map and the unique map into the terminal, and if I map those under I, then I get a commutative comonoid in C, and this satisfies all the relevant compatibility conditions, so I do get a Markov category. A Markov category has a deterministic subcategory, and I get a factorization of the thing I started with V through that deterministic subcategory. So this isn't necessarily faithful. This one obviously is. And just to mention, what I've defined here is actually nothing other than a commutative Frey category with over the original Cartesian category whose unit is terminal. So just to close the loop, so one way to get one of these things is to start with a monad on Cartesian category V. It has to be a commutative monad and an affine. So an affine monad is just one that sends the terminal object to a terminal. To say what a commutative monad is, it's analogous to what a commutative clone is, although you need an extra structure on T to be able to say that. You need strength, you need T to have a strength. So I won't talk about that further. It's there. Okay, so and this example essentially contains all examples of Markov categories for the following reason. If I take a sort of probability theory in the sense of the previous slide, then I can construct an adjunction between the pre-sheaf categories, which induces a commutative affine monad on this one. If I take the Kleisli category of that and restrict it to the representables, then I get something which is just what I started with. Okay. So in particular, if I had a Markov category, I could take B to be C sub det, and I could put C det, C here. I could get an adjunction and then reconstruct the Markov category as coming from a monad. Right. So why do we have the definition of Markov category like that? So it's so that we can forget the Cartesian subcategory we started with. We have a maximal possibility, this wide subcategory of deterministic things. There's some advantages to this because having the Cartesian subcategory determined by equations means that you can prove things are in it by doing equational reasoning. Whereas if it's given separately, then you can't prove things are in it like that. For us, it doesn't actually matter. So I'll just sort of keep around category B. So I'll mention this thing we started with, finite sets into fin stock, is an example. And the other main example is measurable spaces and the Kleisli category of the Jury monad on measurable spaces. We won't really need any details of that. Okay. So coproducts in a Markov category. So this is something that happens when you want to consider colimits in a Markov category. You have to be careful how they interact with the deterministic maps. So first of all, a coproduct should actually be a true coproduct in C. We certainly want an actual coproduct in C. The following things are equivalent conditions we can put on it. So one is to say that the pairing between maps out of A, maps out of B to maps out of A plus B preserves and reflects deterministic maps. Okay, that's one condition we might want. Another is to simply say that the coproduct inclusions are deterministic maps themselves, so the copy maps. And another condition is that the copy that's assigned to A plus B is the one you would expect to get from its property as a coproduct. And it turns out all of these things are the same, so we can ask for any one of them. Okay, quick recap on distributivity. So a distributive symmetric monodal category is a symmetric monodal category with chosen finite coproducts. And these canonical maps say that, which are isomorphisms, which this tells you that the tensor distributes over the plus. And a shorthand is a distributive category is a Cartesian category, which is distributive as a symmetric monodal category. That's standard terminology. Okay, so now a distributive Markov category is a distributive symmetric monodal category such that the chosen coproduct inclusions are deterministic. Right. And now here's another way to think about that. So another throwaway definition. Start with a distributive category. So that's a Cartesian category with coproducts and the product distribute over the coproducts. Distributive probability theory over V is an identity on object symmetric monodal strict functor into a symmetric monodal category whose unit is a terminal such that this functor preserves finite coproducts. So as before, you get a Markov category, and in fact, because I preserves finite coproducts, C has coproducts as well. And because V was distributive, the canonical maps go to C are still isomorphisms, so you get a distributive Markov category. And because they were in V, they're deterministic. Yeah. Okay, basic example is we take a commutative affine monad on a Cartesian category V, but if V is also distributive, then the Kleisli category is automatically a distributive Markov category. And let's think about a sort of converse. So if I have a distributive probability theory, I can construct an adjunction like this. So this is the category of finite product preserving functors from the opposite of the intercept. So it is the free colimit completion of V that preserves the existing coproducts, existing finite coproducts. This gives a monad on this. This contains the representable functors, and the restriction of the quasi-category to the representables is just the thing I started with. So distributive Markov categories, really, it suffices just to consider monads on distributive categories to get all examples. One more thing to notice. If I let V be finite sets, what are finite product preserving functors from thin op to set? That's just equivalent to sets. So the only way to get a distributive Markov category over thin is to have a commutative affine clone. Okay, so note, both the examples we had before are already examples of distributive Markov categories because thin and mesh were both distributive categories. Right. Okay, if I have a distributive Markov category, then I can look at the image of the finite sets in it. Okay, so the numerals are the objects which come from the canonical functor from finite sets into C. So that's the empty coproduct, the monoidal unit, the sum of the monoidal unit with the self, and so on. Okay, so that means that every distributive Markov category induces a clone. And it's going to be a commutative and affine clone, right? C sub m. So concretely, it's an algebraic theory whose emery operations are the distributions on the finite set M that C thinks exists. If I take our two main examples, fin stock and stock, the induced clone is just the ordinary clone of distributions that we started. Okay. So when we program, we sometimes want to actually run our programs. So Markov categories are very abstract as they are. They contain a lot of objects that we might not know how to implement, but our distributive Markov categories contain the numerals, and we know what values of those should be. So if we have non-deterministic maps between numerals, we'd like to be able to run those, treat those as an actual probability distribution or family distributions. So what we call the Bernoulli base is a system for doing that. So if I have a distributive Markov category C, the Bernoulli base is the thing that tells me how I run its programs at ground. So that's an injective monoidal transformation from the numeral clone into the clone of distributions. Okay, so it's a monoidal natural transformation. Equivalently, it's a clone morphism by what we said before. So concretely, it's saying each sort of state on the finite set N in C gets identified with a classical probability distribution on N. And I was looking at our examples, fin stock and stock. Because the numeral clone is actually D, you can check there's a unique Bernoulli base, just the identity on D. That's the only way to identify its numeral programs with classical probability. Okay. Now we can actually program the graphs. Okay. So let's see the distributive Markov category. So graph interface is the internal version of a black and white graph from before. So it's a chosen object B in C, sort of an object of vertices. It's a map B tensor V to 2 called edge, which is the edge relation on V, and a map nu from 1 to V. So you can think of that as a measure on V, or in programming terms, it's the command that samples a fresh vertex from the set V. And we have these conditions. Edge should be deterministic. It should be the adjacency matrix of a graph. And it should also be irreflexive and symmetric. So that's this is what those mean in terms of equations in the category. So irreflexive means if I start with something, if I start with V, if I copy to go to V tensor V and then edge to go to a Boolean, that's the same as starting with a vertex V, discarding it, and then just going straight to true, so straight to false, sorry. And being symmetric says, if I start with V tensor V, I can use the Cartesian subcategory to swap those two things, and then edge, that's the same as just doing edge without swapping first. Right. So suppose I have a distributed Markov category with a graph interface. Okay, as before, I can look at finite simple graphs as an Oplaks monodal functor into C, going via the subcategory of finite sets. And I can then define a monoidal cone over this in C with the following program. Okay. So the program takes n new samples. So this is the probabilistic part. It does a deterministic thing. It makes copies of the vertices and pairs them up. So I've got all n choose 2 pairs of distinct vertices that were sampled. And then we do another deterministic thing. For each pair of vertices, we replace it with its edge predicate to get a Boolean. So now I have n choose 2 Booleans, which is the same thing as having a graph on n things. Okay. Right. Essentially the same argument as before. A monodal cone is the same thing as a monodal transformation or a clone morphism from G to numeral theory. So if my category has a Bernoulli base, then I can go from G to numerals to distributions, which is a random graph model. Okay. So now there's the question of the converse. If I have a random graph model, can I find a Markov category with a Bernoulli base, a distributed Markov category with a Bernoulli base that gives me back that random graph model? So here's a simple partial answer. So recall that graph ones were valued in 0, 1, the interval. If I take one that's valued in just always false or always true, then I can use stock as a Markov category. I give it the graph interface where V is just the omega, edge is this, U is the uniform distribution on omega. We know it's Bernoulli based in a unique way because the numeral theory was spin stock. And actually the graph model we get is the usual one you get from this graph one, if the graph one is black and white. If the graph one is not black and white, then the edge map we define here is not deterministic. So what about general things where I don't assume the graph one is black and white? Right. So here's a way of constructing such a Markov category. We do it in 2 steps. So first of all, we find something that models the vertex edge part of the interface, but not the new part. Okay, and this is simply the free finite sum completion of the opposite of the category of finite simple graphs and homomorphisms that preserve and reflect the edge relation. Okay, not necessarily injective. Objects are sequences of finite simple graphs, which you think of as being the sum of these n different things. Okay. This is a distributive category. Okay, so here's proof by example. We're going to choose V to be the one vertex graph. The product of V with itself, if you think about it, you'll see the product of power V to the n is going to be the sum of all graphs on n vertices. So in particular, the product of V with itself is the sum of the graph with an edge between 2 vertices and the graph with 2 vertices and no edge. As another example, the product of those 2 things, if I wanted to calculate it, is the sum of all graphs on 4 nodes which restrict to that in one side and restrict to that on the other side. Okay, but with this description of the product, I can say what the edge map is quite simply. The edge map is going to be the thing that maps the left half to true and the right half to false. Okay. Right, so that models vertex and edge. We'd like to add a global element to a set of vertices. So there's actually no map from the terminal object into V in this category. So we'd like to add one freely. So this was done with a universal property by a meter-tenant for non-distributive symmetric monodal categories. So we need to modify that a bit to get something that preserves distributivity. So the easiest way to say what it is to define the Hom sets in the case where the domain is just a single thing and not a sum of things, and then extend by distributivity. So the way you get a map from a single graph G into a sum of graphs is you pretend you have, for some k many vertices lying around, and then define a map. Okay. Right, and then you can check, and this indeed works, and we can define new a map from the terminal to one vertex graph by picking k to be 1 and projecting off the terminal. Okay. And actually, if you now compute the numeral theory of this distributed Markov category, we get the clone we had before, clone of graph sampling. Okay. So we're almost there because we have a distributed Markov category, and every functor, every clone morphism from its numeral theory into distributions gives you a random graph model. But we wanted a Bernoulli base to be a faithful functor. So fortunately, we have the following theorem. Suppose you have a distributive Markov category and a functor from its clone theory into distributions. Then you can quotient it to get another distributive Markov category whose numeral theory injects into distributions. Unfortunately, there's an extra condition here to make the coproducts work. So, but fortunately, that holds for us. And the idea is to say that two morphisms are equivalent if there's a contextual equivalence between them. So every extra context Z, every sort of closing substitution, and every measurement you can take, the functor psi gives you the same thing in the end. Then you say that they're equivalent. Okay. So just to summarize that, every random graph models are precisely the same as clone maps from the numeral theory of this distributive Markov category into distributions. And because we can quotient, we get the following theorem. Every random graph model arises from a graph interface in some Bernoulli-based distributive Markov category, where graph interface is an internal notion of black and white graph to a Markov category. Okay. Right, so to conclude, I hope this shows categorical structures are quite a good match for the algebraic constraints that random graph models had, because it was precisely being a monoidal natural transformation or a clone morphism that corresponded to the restrictions. Distributivity is a very natural thing to add to Markov categories, and like some of the main examples already satisfy this, simply because any monad on a Markov categories that come from monads on distributed categories are going to be distributed. So one thing to note about this result is that it's very indirect because of the quotient. It doesn't really tell you how to run these programs. So in the special case of the Erdős-Rényi model, our paper contains another interesting construction of the category that gives you a graph interface, that contains a graph interface that gives you that model. Using the topos of Rado nominal sets. So that's the topos of continuous actions of the automorphism group of the Rado graph that I showed you earlier. You sort of, if you interpret probability theory in that, then you can get interesting measures on the objective vertices of the Rado graph. And you can use that objective vertices as the objective vertices for a graph interface. So sorry I didn't get to talk about that as well, but I recommend looking at that later. Okay, thank you very much.
We've got time for questions, so does anyone have one? So can you make three models happen by just have the injecting functions of their opposite category? That's the same.
So free models of what?
Sorry. So let's say three same Cartesian model categories. the category on free in the sense that the category of semi-Cartesian categories which have discrete structure. So if
Mhm.
the free structure, then make these free constructions.
Yeah.
And I'm wondering if you can make these kind of Markov categories in this kind of free way. Is there any interest in that?
Yeah, there is interest, and other people have looked into free Markov categories. So for us, we needed the freeness to include the distributivity, which we couldn't find already done. And we haven't really formulated any general theorems about when they exist, just constructed our one. But yeah, no, it's a good question, and an interesting one, yeah.
I'm in the business of
Yeah.
These structures.
Yes.
Yeah.
Yeah. And I think there's interest in universal properties, not just for the strict functors as well. A lot of this, the strict functors were actually the right thing to look at.
Brilliant. So, you mentioned how sometimes the Bible graph can give as a 0, 1.
Yeah. Yeah.
Then I guess so. Then what we're finding out here is that we start doing stuff over. Okay, so if we start looking at all the distributed Markov categories, then like 0, 1 graph ones.
Yeah. Yes. Yes. That's what I'm saying. Yeah.
That's.
Yeah, it just I don't know. You could say categorical probability is flexible, or you could say it's not strong enough. You know? Something to think about. Yeah.
Is there an intuition why you can do it?
I don't have a good intuition other than the technical proof, which is you say what an equivalence between graph ones is, and it's like a measure preserving function between the vertex objects. So it's not just a single function, it's a zigzag of things in general, but then you can normalize things and then check that if you can present it with a gray thing one way, then you could never end up presenting it with a black and white thing. So yeah, that's quite mysterious to me still, why you can't do it.
Can you start by saying that the graph is like set with an irrespective symmetric
Yeah.
relation? How much of this story would adapt if you were to have a drop symmetry or have a ternary relation or like other possibilities? Was it very specific?
Yeah, it's a very good question. It should work. One reason for doing this was that there was already a lot of theory on this very particular thing, which we could compare it to. It seems like there are odd subtleties that come up in the general case that maybe you don't see quite enough in the special case. So I'm not convinced it completely goes through immediately. I think the same kind of results are true, but they might just require slight tweaks. But another issue is that it's maybe not clear exactly how the graph programming interface corresponds to a class of relational structures. There's something there as well. Yeah.
So it's great to talk really like that.
Thanks.
So you kind of have like a definition of graph interface in terms of diffusion. I was wondering if there's any other cool examples of Markov categories in which graph interfaces have nice incarnations.
Well, this one is very nice and rather anomalous. Is that sort of thing? Yeah. So this one is interesting because it almost looks a bit like standard probability internalized to another topos. And it's saying if you choose a non-standard set theory, then you can look at standard probability and present a graphon with a black and white graphon, which you shouldn't be able to do. That's not quite true because it's not actually standard probability. So it's probability where you have countably additive measures defined on the full power set of a set, which is not something you normally do. but it's a little bit close to what we normally do. Yeah.
What kind of calculations would you like to have? So let's say this project, then we have things go. What kind of what do people want? Or what are the applications?
Most of the practical applications are actually not about dense graphs, but sparse graphs. I think there might be some with dense graphs. So we'd like these models to tell you how to run these programs. Our abstract thing doesn't actually tell you how to do that, which is so there's sort of still a search for other kinds of models to tell you how to run them. I guess the main point here was to give another perspective on this like well-studied class of things, to say we can characterize what they are using this other machinery.
Maybe it's interesting that this categorical language is really well.
Yeah.
Any last question? Yeah. So you started with these graphs and here, with angular distance.
Yeah.
Just only take different setup. Different graphs isomorphic.
Sorry, take different what? Different. Oh, okay, yeah.
Boundaries.
That's a good question. Yeah.
And you consider a lot of these.
Yeah. Yeah, it's a really good question. I don't actually know the answer, but no, I wanted to, but yeah.
Let's factual again. Let speak like to come up. Slides up. Yeah. These ones, yeah? Just open them. How do I go? How do I pronounce your first name? Gregor. Okay, great. So Gregor is now going to talk to us about composition statistical mechanics, entropy, and variation. Inference.
Okay, thank you very much for having me. So it's kind of related to the first stuff, which is good. But it's a bit different in the setting that we're considering statistical mechanics, which is known to basically generalize many probabilistic modeling. Let's say at least when you have interaction between a lot of variables, you have so collection of variables and want to study like probabilistic interactions between them. So we want to say that basically there are dependencies between variables. And so, for example, which we'll introduce most of the time is an energy, which corresponds to how likely is the confirmation of a couple of variables. So, for example, something like this, you have a line of variables, and then you're going to say that x1 is dependent on x2, x2 is dependent on x3, and then you do it by summing potentials, like local interactions. This gives you when you use a Boltzmann distribution, so a weight at exponential minus certain coefficient beta h, factorization of the distribution that you can identify as a Markov chain. And so you have many like probabilistic models and graphs like this that fall into this setting. It's a very well known setting in physics. And it has, of course, many applications in computer science, mostly probably most of you are familiar with Markov chains and hidden Markov models, how they are used in computer science when you want to do inference on time series, for example. And you have more generalization to it, which is graphical models, which are part of the cases of statistical systems, factor graphs, and all these kind of cast of systems. When you want to do inference on this, you need to a very famous algorithm, which is the propagation algorithm, which is basically one of the main domain of machine learning that's not. And there's a mathematical theory to try to understand these systems when you have a number of variables that is infinite, that is countable infinite. So basically, when you have one entity, one Hamiltonian, and you want to define distribution, so make sense of this quantity, it's not direct. You cannot do it directly. In fact, you can have something that is kind of interesting. So if you want to formalize it, you need to introduce what is called DLR condition. And something that is very surprising is that you can have for one Hamiltonian 7 distribution is what you commonly know as phases or pure phases. Depending on the temperature, solid, gas, liquid, so if you're at phase transition, you have different pure phases. So this is something that is you could not describe with the finite, unless you get with the finite setting, and this remark necessitates to introduce new mathematical machinery, which was well understood like O'Neill and like it's something from the I think well studied and understood for some time already, so more than 30 years. But you still have hard problems in it, which is basically characterizing the phases. You know how much pure phases you have. And manipulating the phases is difficult. So what I mean by manipulating, familiar with this coarse grading, for example. So it's something that is and actually that is very, very, very fundamental, which is that you have a translation environment potential. So it's something like equivalent to saying that you can compute variables. To make a little bit of first talk, if I understand correctly. So you have a correspondence between phases and tangent of a certain convex functional, which is Helmholtz free energy, which is that you can characterize as the phase transitions of a system with respect to looking simply at a convex function. And this is called variational principle. This is the dual version of it. So now I will give some definition of what statistical mechanics is. And we'll see that you can give a more local formulation of it. So you consider a collection of an index, so collection of variables, I that is. So I will consider finite random variables. You will need to just not to have to introduce some analytical subtleties. But I is countable, not binary. So you have a collection of random variables that they value in space EI, which is finite space. One, you have a global state space, which is a product of variables. And then you have a probability distribution, like a space of measurable space of probability distribution, which is key. For any finite collection of subsets, you have maps that corresponds to forgetting about variables. So if you have B increment A, then you can always project the variables that you have in A, so variables that depends for xi for I and A, onto variables that depend that are only in B. Okay, so you have these natural maps. We like the projections. And now if you want to introduce a statistical system, what you need to consider are border conditions. So border conditions are basically a way to say, if I fix what's happening outside of the finite size system, like if I say I want to simply model what's happening inside of this circle, I have a collection of variables, finite amount of the variables and condition all what happens in the border. I want to say that this is my way of experimenting with the system, so I will use it as the input. I have a kernel, so probability distribution for each configuration that I have on a bar. So for each node is a variable. So for each variable in a bar, I fix them. I give myself a probability distribution on what remains on the A. So this is called the probability kernel. It's a particular case of probability kernel because it respects a property, which is that basically if you have things that depend only on what you condition on, then if you try to make an experiment on it, it doesn't change the function. So this is called proper kernel, means that if I plug in inside of my kernel a function that is measurable only with respect to what happens on the border, then in this case, it doesn't change the function. So this is the first ingredient you need to plug in to try to abstract the idea of the statistical system. The second one is the chain rule, which is basically the condition the border and then you condition on a small border. Then it's same thing and conditioning directly on the small border. Okay, this is called the chain rule. And if you plug in both, then you have this kind of more general formalization of a system, which is a collection of kernels that are proper and that satisfy the chain. So here, what is it? Something is, if you see it this way, I mean, there should be a map between both, but you don't see it here in the middle, which basically tells you that you send things that depend only on the, so here when you do this, it's a measurable map on all the variables, and then you send it to something that is measurable only on the variables that depend on the bar, so that are in the bar, and then you should have a way to re-plug them back into the space of all the random variables, functions that depend on all the random variables. This is something that is direct because there's an inclusion, and so you don't put this. And so this can be a bit, if you don't put it, it kind of hides a lot of stuff. But this is how it was, it's how it's most of the time. So these measures are measures that are compatible with respect to the collection of Markov kernels, which is simply saying that if you give yourself a distribution such that when you put your expectation on the, let's say, variables that depend only on the bar, you find back the kernel that you have. So Gibbs measures are compatible measures with respect to the kernel. So the kernel is called a specification. The collection of kernel is called the specifications. So, and so the game is to try to characterize this measure. So now, what is the idea? Why you want to try to find a bit more local perspective? Is because when you have a global reference, really is difficult to some like I said, I mean more precisely, to be more precise, if you describe statistical systems from a Hamiltonian perspective, you don't have it doesn't behave well with respect to maps from basic, let's say, measurable maps between the spaces. And even worse, if you decide to do local operation on Hamiltonian, like summing, adding potential, adding interactions. In this case, it doesn't relate correctly. I mean, not in a very simple manner, in a very difficult manner on how you apply transformation functions. So if you add a potential to a Hamiltonian, it doesn't change the compositional manner, the measure of the Gibbs measures for the Gibbs specification. So the idea is to try to instead change the perspective, forget about the Hamiltonian, focus on the specification, and try to build from simpler statistical systems by gluing them together more complex statistical systems so that you can have a controlled manner to compute the phases. So that was the initial motivation. And another motivation that comes more from, let's say, machine learning is that if you allow not to look at all the variables at the same time, you have some bunch of variables that you can look at the same time, but not all the variables at the same time. This introduces some kind of heterogeneity, some kind of incompleteness, and it can also be incompatibility between the observations that you make. The statistical system cannot account for this, and this goes in the direction of using sheets in data science, which cannot go back to Curie's thesis in 13 and has seen many recent developments, but it's not strictly the same. Okay, so we said the specification is basically a collection of kernels, which are the black lines, and a collection of projections, which are the dashed lines. You need to see both, that's why you have both, and you have a measure, which is simply something that goes, so it's probably the kernel from the point inside of this measurable spaces E and C, A. And what you want to say is that this is basically a code over something. Your code over something, so that's you can complete, have blue lines here, and forget about the code. So you don't want to refer to the global space. You want to say maybe there's an underlying structure on which, so basically a function from something to something, moves it to something, so that I can forget about what's happening. So you need both. What is a key point is that you need both structures. You need to have Markov kernels, but also projections, or let's say a function that goes into a measurable space. So this proposition tells you that we can extend a specification in a unique manner into a certain function that goes from the closed set, so we pose it up finite sets inside of I to the category of Markov kernels. So the category that sends which have as multiple maps and as morphisms things that sends to points probability distributions, and then you can show that it's immutable. So these are the two categories that we play. So the first one is category measurable spaces. Maps are measurable maps, and kernels have the same objects but Markov kernels as morphisms. So the more general, like the definition, like generalizes what we studied, what we just saw before, that I proposed is simply considering a couple of a functor, a free sheet that goes from a poset inside of the space of integral spaces and a functor that goes inside the space of the kernels, and have this kind of idea that F is a section of G. I mean, if you see it unobservable, it's more G that is a section of F. It's just a way to keep in mind that F has to be proper. Here, let's say that we completely forgot about the biograph collection of arguments. And A is not a sub-collection, it's not a collection of subsets of arguments. So what is interesting in this formulation is that most of the time we don't have to constrain that much A, but we can constrain, and this is what I will do in this presentation, we can constrain the images, which is basically that GA, they have, the GAs are finite sets. So the spaces in which you take values are finite sets. And here the domains of F and G are the objects. So it says an element of the process for an object. F, B is the same thing in G, B. So that you can compose. So now we have this picture, which is that we transform the specification into a collection of functor and a free sheet, and they have to be sectioned from one another, so we can forget about what happens above, because in fact you have the next definition, which is generalization of fixed methods that are simply the ones that are in the middle. So it didn't say much, just one little property is that you can extend it, and then you say I'm going to do more standard stuff. So now you get with the fact that you're looking at the different subsets, so you have environments, you get cohomology groups, you use resolution to compute HUO. In particular, interestingly, when you want to do it, you have two kinds of objects, projected and objectives. Here I'm cheating, but I'm not quite cheating. But yeah, because it's projected, but projected in one sense, because in the post you can inverse the order. So projected for one order is not the same when you do it. But in any case, so projected injectives are related to what is called the interaction decomposition mechanics, and sorry, in models, it's related to the chaos decomposition mechanics. And projective objects, in fact, very interestingly, they are generalization of what are independent variables. So what are projective objects or posets? Simply are there things that can be decomposed as sum of things, so that when you go from A to when you go to B. So here I changed. They explain why, but because most of the time you don't go on the states and the measures on the measurable spaces considered observable. So the space of continuous function of spaces or infinity functions from the spaces. So this is really the picture to keep in mind, which is that if you have you want to say that some Markov kernels induce some projections on observables, and then the projected free sheet is simply something that can be decomposed of sum of parts, so that the projection induced by the kernel is simply the projection, standard projection that you have from the sum of parts to a restricted sum of parts. So this is the standard definition of a projected free sheet for a poset, from poset to the category of vector spaces. Okay, and you have a characterization of the system, which is when you have meets. You can say that you can show that projected free sheets are in fact simply one that satisfy this property. So this is something I did in my PhD. I don't know if I didn't find the result elsewhere. Maybe it's something that is very known that I don't know about, but for the moment I will be told that this result. If you have an idea, it's coming. So to give an example of what is a projected, okay, so cool. Just to give an example of what the projected free sheet is in general for a poset representation. So for function from the free sheet from the poset to vect, consider these three vector spaces. So V1, V2, V3. So you start with V0, and then you have V1. So you have the basis V0, V1, V2, and you look at the vector space, the line generated by V0, the plane generated by V1, V2, and you see that you can project on the big space to each of the two planes and then to the line. Okay, this is used. But more importantly, here you can decompose it as projection only over the vectors that are not, so in this includes the vectors that need to add to generate the plane. If you change the scalar product, this property completely fails. So if you want to see a statistical system as a system of projections, you need to see it as simply collection of planes which corresponds to observables. And then the projections are simply the conditional expectations on these observables, so that you replace the distribution by projections, and the projections are exactly what specification. So now, the way you put more formally is simply now you consider f, which was a pointer from A to kernel, and then you compose it with saying that to any object you're going to send the space of any like bounded function on it. So we assume here that you go inside of finite spaces. So the f of A is finite, or else you cannot. It's not anything to consider. And what I would say a projected A specification, so just something that behaves like a projected tree sheet, is an S specification, so that when I embed F inside of X, so when the identity that goes to the category of mark kernels to the category of vector spaces, this is projected. Okay. Now you would say, okay, H0 is trivial, and then all the rest we care. But as I told you, there's a problem, which is that it's projected, but not with the right order of process. So you still need to do something if you want to characterize the limit of F and give measures on that, even in the case where F is. So it's something that I didn't put, and that it's something that I haven't noted. I didn't put it online because I'm sure it's interesting you. I mean, in any case, if F is projective and you consider like the cohomology group for the reverse order, so you just propose A. In this case, you have that H0, H1 do not cancel, but Hn for n bigger than 1. So you have a characterization that gives measures for a projected specification, which is just the classical one. You just consider like the terminal objects inside of A if you have a unique connected component. But what is interesting with this result, it's not saying that you can always write it like this. Is you say that it is the only ones, or else you don't get anything. So the strong part of this one, saying that you don't get anything if you don't have terminal objects. Okay, so now I just described a bit how we can play using this basic homological algebra, which is the only thing that you do. So when you study statistical systems from a different perspective, and I will try to give a new flavor, like not new flavor, like some new perspective on it. Try to extend some very important properties of these measures, which is called the zero-one law for extreme case measures, which I will explain when we get after. That to the categorical setting, to the case where you consider specifications as follows. So something that's very important about the random fields is that if you consider collection, if you consider what is called the tail sigma algebra, then you have most of the time a lot of large numbers to apply to them. This is essential for studying random fields because it allows you to tell you that you have an infinite number of variables, and then you consider observables that are basically global property of your systems, then you can be deterministic when you measure your probability distribution on these observables. So this captures the law of numbers. This captures it captures like the arithmetic decomposition of chain. It captures many properties on the infinite size behavior of statistical. So how to say this precisely? So now consider the simple setting where I is equal to n. Just this is what the standard formulation, but you can do it when n is not it's not n but I anything. And you need to consider an object filter, but it's okay, standard. So then you just have you consider the sigma algebras of things that depend only on the variables that are bigger than you. Okay, which is basically you just consider cylinders, things that if you take variables that are lower than k, you consider any possible value. So you take sets which are of the form E1 times E1 times E2 times up to k times k. So this is called I will denote it as the sigma algebra generated at what is above k, and the general sigma algebra the intersection. It means that you look at variables, you could think that this is very trivial. It's not trivial at all. Contains a lot of stuff. There is a sigma algebra that contains measurable functions that do not depend on only a finite collection of variables. That means that you can change your system as much as you want. For a finite number of variables, the observables will not change. So typically 1 over n to the sum of xn, you know that if you change x1 to xk, it doesn't change 1 over n to the sum of xn. Okay, and the set of the Gibbs measures is convex. I mean, this is just a statement to say it explicitly because I didn't say it before. What is interesting is just that any Gibbs measure is fully characterized. So for a given specification, you can distinguish the Gibbs measures by simply restricting it to this Taylor sigma algebra. So that's nice because it's neat because it's much more than the global sigma algebra. It's kind of big. And extreme Gibbs measures, extremes in the sense of convex sets, are exact, which are what corresponds to physics. Pure phases are trivial on the sigma algebra, means that they give you 0 or 1, which is called the 0-1 law or 0-1 law of physics. So I think you have a lot of different things, depending on the process you're in. And so this is what we're going to try to reproduce for in the category setting. So just like it calls what was the specification for us. So it's a functor from so appreciate into measurable spaces, functor into Markov kernels. I assume that GI are the GA are finite. I assume a positivity condition on it that I do not precise here. It's okay. So and but I think you don't need these assumptions if you want to get a weaker version of the zero. So this you just need this if you want to represent the measures in. If you want to find something like choosing a reference measure, having a function this that is measurable. So if you want to say that any Gibbs measures can be written with respect to reference measure, you need to introduce this. If you don't want to do this, you can have a weaker version of it. And so what replaces the Taylor sigma algebra is basically the thing that is in the limit of G. I mean limits of not of G, but the functor induced by G on the sigma algebra. So how is it defined? You take a subset of B, and then you just apply G minus 1 on it. This extends to a map from subsets of GA to subset of GB, just putting back the sets. Okay. And you define so this is the function, you define the limit of this, and this replaces the sigma algebra. And then of course you get the extension theorem that tells you that these measures are convex uniquely, so these measures in the as a limit of a functor of f, of a specification, or a specifications, they are uniquely determined by their restriction to the equivalent of the Taylor sigma algebra, and furthermore, they are ephanoidal. They have the 0-1 law, but the 0-1 law that does not depend on defining a global spaces. It's only a 0-1 law on something that is in the limits of things that are local. So you can always act on this. It's not the same thing I'm trying to get building a representation of the specification as a distribution on a global space, because this is difficult and you cannot always do it. You stay local and you define the object locally, and so I think it's kind of interesting. For me, it was kind of a nice result to know that we can extend it. And of course, it goes with the 0-1 law, like recent work on the intercategories for IE sequences and Markov chains, and one of the first orators who contributed to the ones of Markov chains. But I don't have a full understanding of this work yet, so maybe it would be a nice way to explore it a bit more. And if you want to know how to define, or at least this is more tools than the first part. The first part, I think, is kind of a full picture. But if you want to have a more an idea of, so if you want to define the notion of entropy, so that you can define the notion of variational inference. Variational inference, sorry, depends on entropy. Defining an entropy for base expectation, not clear what it means. And I tried to give some elements in this direction in section 8 of the paper, on which is the sufficient space. I would like to thank you very much for that.
Questions?
Yeah. So there's correspondence between statistical mechanics and quantum field theory in one dimension, and then there's quick rotation. I was wondering if this framework can say about quantum field theory.
So what do you mean by the correspondence? Maybe I'm not familiar with this correspondence.
I think it's something like if you take time to be imaginary.
Yeah, the weak first. Okay, so
I was wondering if this is how we can say about it.
So exactly, this is for statistical field theory and not for statistical mechanics, which is more general. So the thing, in the sense that it's more general, means that it's probably less difficult because you don't have to introduce differential operators on random fields. So the correspondence mathematically is very difficult. And so I try to look into it, but the thing is, as you need to define random differential operators on random fields, is difficult. Okay, one answer in this direction is, so projected, the injected the injective, say, three sheets that you have here, which I said related to. So just, no. Yeah, no. So here, the injective, so I told you about the projective, you have something with respect to the injective, and so I said it was related to the chaos decomposition. In fact, there's a way to relate chaos decomposition to the ordering, like 2-point ordering, with big ordering and on the previous comments. So, okay, so basically if you want to do gratuitous QFT, you need to do an extension of the operators, and there's a relation between the chaos decomposition and this ordering that you need to define. And so I think this is the direct way of extending the results. And in fact, I try to work in this direction, and I think it's very nice. So I think it's possible, at least for the perturbative case. Cool, thanks.
Maybe just have time for one more question. Okay, well, it's time for coffee break anyway, so we'll start the coffee break and we can chat together in the break. Okay, let's have a go. We're going to have a group photo. We're going to do it outside on this patio. Yes, I want to start holding my hands. So, now, and then we'll have coffee break. Okay, so please head outside.